point that is worth making note of is that the electric force is conservative. If you remember way back when we were talking about work and energy, we talked about conservative and non-conservative forces. A conservative force is one that conserves the mechanical energy of an object, meaning that it just it can change energy from potential to kinetic, but it's not going to take any energy away, and it won't go off into heat or sound or anything. It will remain in the object in the form of kinetic or potential energy. And conservative forces, which actually all of the fundamental forces are, can be described with field lines, or diagrammed, I should say, with field lines. Now we know the electric field points away from positive charges, points toward negative charges, and that gives us our basic guideline for drawing electric field lines. There are a few rules. The field lines point in the direction of the E field, as one might guess. And I'll give you some examples of what this looks like. Point in the direction of the E field. They start at positive charges or at infinity, and then they terminate at negative charges or infinity, and they are denser where the E field is greater. And practically what that means is that there are more lines coming out of or going into larger charges. Okay. Now, it's not a perfect representation, because if you draw the field lines correctly, you will see that they get further apart as you move away from a charge, but they don't fall off with the r squared as they should. So if you just have a positive charge chilling around, our field lines point in the direction of the E field. E field points away from positive charges, and they start at positive charges, and then they end at negative charges or infinity. Well, if there's just this positive charge, then these will just, you just have lines pointing directly away from the positive charge in all directions. They are continuous lines, so they're not like, you don't draw an arrow at each little point. That would be that's a different sort of thing, a vector field, I think it's called. And then they're denser where the E field is greater. You can see these guys are closer together as we're closer to our charge, and then they're further apart as we're further from our charge. But the density doesn't go with 1 over r squared, so it's not a perfect representation, of course, but it works out pretty well. If you have a negative charge, say this has a charge plus q, right? And then say we have a negative charge, and this is a new example, it's not connected to this one. Say we have a charge that's minus 2q. This is minus 2q. It looks almost identical, except the lines are pointing toward the charge, and 2, because it's minus 2q, it has double the charge. There should be double the number of field lines coming out of it. So there will be twice as many as a plus q. There isn't a standard amount of lines that you use, but in any given diagram, the number of lines should be proportional to the charge. So if you have a plus charge that has, say, 4 lines, then if you have a charge that has 4 lines, a charge that's double that should have 8 lines, and so forth, right? So we're going to look at, when you're drawing these, it's not important that the lines are perfectly curved how they should be. Like, you don't necessarily know what that's going to look like, but qualitatively they should be correct. Let's consider what happens if we have a positive charge and a negative charge. This is called a dipole. when you have two charges of opposite sign and equal magnitude. They share the same number of lines, and they point away from positive charges toward negative charges. So the one in between just goes straight, from the positive charge to the negative charge. Now, if it was just the positive charge, we'd have a line going off this way, off until infinity. If it was just a negative charge, we'd have a line going this way, off until infinity. But because the negative charge is here, what the positive charge would do, it kind of gets pulled down toward the negative charge. And so you wind up with it looking something like this. So when you drop a new negative charge into the field, you can say that the lines get pulled toward it, kind of. And if you add a positive charge to the field, you can say the lines get pulled away from it. And this would go on like that. Then we'd have one like this, and it would curve around. I'm just not drawing it, but it would go all the way around here. And then like that, and then the one that goes directly off would actually just go off. Those aren't going to connect if it is going off in a straight line. It's kind of what it looks like. And as I said, it doesn't matter if you get these curved just right. What's important is that they are qualitatively correct. Right? So we can do multiple different charges. Let's say we have a minus 3q and a plus q. All right? And in the interest of not drawing a bajillion field lines, I'm going to do just four lines for the plus q. So there will be a line that does this. And this will go off like this, but it'll get pulled toward the 3q faster. So this field was symmetrical, but this one isn't going to be, because the 3q is bigger than the q. And it'll look something like this. So then those are the 4 lines coming. Oh, those are 5 lines. Shoot. Okay. If I made 5 lines for the plus q, and that means I need 15 lines for the minus 3q, but the rest of these lines shouldn't terminate at the plus q. And so, they look something like this. And as I said, technically you should make it so that there are a total of 15 of them. I don't know if I have space for that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh, look at that. I think I made 15. Yeah, so that's how you should work out drawing that. Like if you have say you have a plus q and a plus 2q. The 2q should have double the lines, and what's going to happen is the lines start to go like they normally would, but then they kind of get pushed away by the 2q. I should be more like that. And they'll spray off into oblivion. And then like one here that would go straight up gets pushed away. And likewise for this one. And then this one would go off this way, but it kind of gets pushed. And this is the same thing on this side. Right? And since I put 4 arrows from the plus q, I made 8 arrows coming out of the plus 2q. So you can use that principle to draw field lines for just about everything. There's a particular device, and we'll use it more when we talk about circuits, but a parallel plate capacitor is a device that's used because of the electric field that it has. In a parallel plate capacitor, there are 2 metal plates. So there's metal plate number 1, metal plate number 2. They're separated by some distance, whatever. They're pretty close together. Typically this distance might be like a millimeter or so, or a couple millimeters, maybe even less. And one is given a net positive charge. The other is given a net negative charge. Okay. And they're the same. So there's a charge positive Q here and a charge negative Q here. Generally, this little side note, generally lowercase q is used for a point charge, and capital Q is used for a charged object, which isn't super important, but it explains why I used a big Q here. If we think about this, now right here, let's consider a point out in the middle here. From this guy, there's an E field going down. From this guy, there's an E field going this way. From this guy, there's an E field going this way. This guy, there's an E field going this way. And so in an ideal capacitor, all of these horizontal components cancel out. And so you're left with a field that just goes straight down. And that happens pretty much all the way through the capacitor. At the very edges, it might, do a little bit of bend out a little bit. But in the middle, a parallel plate capacitor has a uniform E field. It points straight in one direction, and it has a constant magnitude at every point in between these two. So it points in the same direction, constant magnitude. This winds up being very useful in electronics because you have that predictable E field, and so when you move when electrons are moving around, they will behave in a predictable way. Capacitors were used in CRT screens, stands for cathode ray tube, which I don't know if you guys even remember, but TVs and computer monitors used to be made the CRT. It's the big monitors, and there were electrons that would be, thrown at the screen basically, and that's what created the images. And parallel plate capacitors were used to deflect them just the right amount to produce the image that was desired.